So greetings, everyone. This is Scott Evans, one of the organizers for NESSIS. Welcome to our next session on probability modeling and decision making. Our first presentation is by Dr. Nate Sandholtz, recently joined the faculty at Brigham Young University in Provo, Utah as an assistant professor of statistics. Prior to joining BYU, Nate did a postdoc at the Department of Mechanical Industrial Engineering at the University of Toronto. And before that, he received his PhD from Simon Fraser University in British Columbia. Much of his research lies at the intersection of statistics, operations research, and sports. And today he will talk to us about an inverse optimization analysis of the fourth down decision in football. Take it away, Nate.
Awesome. Thank you. Okay, let me just get into, all right. So is everyone seeing the
looks good. Looks good.
All right. Hey, thanks, Scott and Mark, for the invitation to speak and for that introduction. Today, I'm going to be talking about the fourth down decision and specifically an inverse optimization analysis of it. I want to acknowledge and thank my collaborators, Lucas Wu at Simon Fraser University and part-time at Zealous Analytics, Martin Puderman at the University of British Columbia, and Timothy Chan at the University of Toronto. Okay, so I'm going to start with a, well, not the fourth down decision, but a decision that likely most of you are familiar with. I've got a screenshot of my phone. This is when I was in my PhD of a Google Maps when I needed to get to my house to the church. And I drove this route a lot over the course of my 4 years of my PhD. And you can see that Google gives me these three routes, A, B, and C, all of which are estimated to be 12 minutes. So what Google doesn't show is the distributions associated with each of these routes. And having taken all of them multiple times, I kind of took the liberty of estimating them myself and put this unimodal distribution over route A and B. But for route C, it crosses, there's train tracks. And if you are on this route and and the train is passing and you have to wait for it, then you could be waiting for an extra 5 minutes, like, which gives this mode here. At 17. And so while the expected value of each of these is the same, the distributions are quite different. So if I'm optimizing here, optimizing on expected value, then it really doesn't matter which route I take. However, if I'm trying to optimize based on a low quantile, say I'm running late for church, which was usually the case, I took route C almost always, because I've got, if I miss the train, I've got a better chance of making it on time. So the fourth down decision, there's some similarities here, where on fourth down, well, in most states, there's only really two viable options to either go for it or kick a field goal or to go for it or punt. In some cases, there's all three are viable options. So I've plotted one of those states here, which is fourth down between the 31 to 40 yard line with 8 yards to go till first down. And what I've plotted on the x-axis here is the expected points, the estimated expected points associated with various possible outcomes of the next state. So you can see like kind of these multimodal distributions for going for it. This primarily bimodal distribution with making or missing a field goal, and this unimodal unimodal distribution over kicking a punt. And the means and expected points of all three decisions are fairly close. But if we plot the sample quantile functions, then we're to optimize based on various quantiles from 0 to 1, then each one of these decisions could be optimal depending on the quantile you're optimizing. So if you're conservative, optimizing based on low quantiles of these distributions, the punt is optimal. It changes at about the 0.4 quantile, where field goal becomes optimal. And then after about 0.7, the go for it decision becomes optimal. So this is just to highlight that depending on your risk preferences, the optimal action could change. So I'm going to go over some prior research. This is by no means exhaustive, but David Romer in 2006 wrote a paper where he asked the question, do coaches optimize expected points? And I use coaches there probably a little too liberally. Like there's more decision makers in play than just the coach, and I recognize that, but I'm going to use that in my talk today. And so what he does in the paper, and this figure really shows his results, is he's got this two-dimensional state space where we've got yard line on the x-axis, yards to go on the y-axis, and he estimates this optimal decision boundary where below the black line, it's estimated optimal to go for it, and above the black line, it's estimated optimal to kick, whether that's punting or kicking a field goal. And so then he plots the observed decision boundary in the dashed line. And obviously there's a big difference between the two, and he said he can say with statistical significance that coaches do not optimize expected points. In 2019, Yam and Lopez had this paper. They say, well, what if coaches had optimized? Well, they actually look at win probability. And they use causal inference to estimate these distributions of the number of wins that teams could have gained from 2004 to 2016 had the teams followed these optimal win probability policies. A follow-up study suggests that these estimated benefits may have been a bit high, but certainly still there. And then finally, another line of research is simply kind of in the business or in the interest of estimating win probability based action prescriptions, where they have some win probability model, and that depends on a multitude of covariates, and they create action prescriptions based on those win probabilities. And so there's a bunch of these. One that I really like and find really interesting is the one by Ben Baldwin with NFL Fourth. And here's kind of a visual of the output of that bot. But one thing I find really interesting is this inclusion of the win probability if columns. And so he shows here the win probability conditional on like a failure of going for it versus a success, and likewise for a field goal attempt, failure or success. And sometimes when you condition on these failure or success, the optimum, if you had known that, would change, of course, right? But to me, that inclusion suggests that risk matters in this decision. And when you look at coaches' actual behavior, it certainly seems that way, where what I've got here is the estimated optimal policy averaging over all other model covariates other than yard line to end zone and yards to go of the optimal win probability policy. And then what I've got here on the right is the most frequent fourth down decision over the 2020 season across all coaches And you can see that there's a big discrepancy, right? Which is, you know, this has been seen in many, many instances over the years. But the question that we ask is, well, obviously they're not optimizing win probability, it appears, but what do they optimize? And so to answer this question, we need a decision framework. So we're going to model the decision as this, you know, optimization problem, where they're looking to take the argmax of this function u of x conditional on as, where x is going to be some representation of future value, conditional on the current game state and the decision. And they're trying to optimize, the decision variable is the action, right? But that future value is random. And so there needs to be some statistical functional whereby we synthesize the distribution, thereby operationalizing the argmax. And so usually we think of this as win probability or like expected value, right? And when we're solving the forward optimization problem, that's exactly what we do, right? Like we choose win probability as the functional, and you know, we estimate the distribution of future value, estimate these win probabilities, and then solve the problem, which results in this, you know, these prescriptions, these action prescriptions. So what we do is an inverse optimization analysis, where our input to the problem is the coach's behavior. And our goal, and we assume that these decisions are optimal with respect to some unknown optimization model. Then the goal of our analysis is to infer the optimization model, and in our case specifically, we infer this functional u, such that the optimality condition holds, or at least approximately holds. So I want to just highlight at this point that like, our analysis is not about prescribing optimal behavior. Rather, it's trying to kind of make inference about a model that makes sense with coaches' behavior. And maybe we can learn a little bit about their risk preferences from doing that. So our approach, first we need to model and estimate future value. We need to define a candidate space of objective functions, or essentially of functionals, which we're going to test in these optimization models. Then we need to choose a loss function, whereby we'll measure distance between a coach's policy and the policies in our candidate space of objectives. And then we'll minimize loss over the candidate space. And finally, we want to quantify our uncertainty about the resulting estimates. So the data for our project, we use two awesome R packages, NFL FastR and NFL Fourth. And from here, we gathered 7 seasons worth of regular season play-by-play from the seasons 2014 through 2020. And then in the NFL Fourth package, we get these action-specific win probability estimates, which we'll use kind of at the end of the analysis. And I'll show that when we get there. Okay, and so first of all, we need to model future value. So we treat the decision as kind of like this one period Markov decision process. And so if we're in a game state, S here, which is a fourth down game situation, we've got these 3 potential actions: go for it, field goal attempt, or punt. And then there's all these potential immediate states that we could transition to. And the rewards associated with those immediate states. But we know that this decision can't be made myopically. Like, coaches are thinking about future rewards. And so we need to model the long run value of a state. And we do so using dynamic programming methods, specifically using some methods from a paper earlier this year by Chan et al. So using dynamic programming, we estimate this value function, which is kind of like the long-term or expected points associated with being in any given state. And so now we can kind of attach this value function to all these possible states that we can transition to from each action. And it allows us to treat the decision as like a one period model. So then we can kind of look at just this immediate, the immediate outcomes and look at these next state action value distributions, which I denote by the capital V +1. And so this plot specifically shows when the fourth down state is 31 to 40 yard line to 40 yards to the end zone and 5 yards to go. Okay, so we need to define a candidate space of objective functions. We use the quantile function to create candidate objectives defined here, where essentially tau, the quantile, just will index the candidate space. And so we basically solve quantiles of this next state value distribution and then take the argmax with respect to A. And so visually what that looks like, if we go back to that, that state we were looking at previously, if we take, here's the next state value distributions, and then what I've plotted on the dotted lines of each of these is the 0.25 quantile. And so then if we take the argmax of all these dotted lines, the punt would be the optimum. If we were to take the medians of these distributions, the field goal becomes optimal. And if we take the 0.7 quantile, 0.75 quantile, the go for it decision becomes optimal. So this is just for one state, right? But what we want to do is to do this for all states. At least, what I'm showing here is the two-dimensional state space of yards to opponent end zone and yards to go. But we're doing the same thing here, where we estimate the quantiles of these distributions and then take the argmax and then plot the argmax in these decision maps. So what this results with is like a tau optimal decision policy, where if we care about optimizing the 0.25 quality quantile, here's what you should do. Here's for the median, here's for the 0.75. And so huge variation, right, in these plots. But you can also see that there's some kind of instability. And this has to do with kind of unstable estimates of the empirical transition probabilities. To attenuate that, we augment fourth down data, or at least the go data with third down data, which is something Romer does in his paper, to help us get a little bit bigger sample size. And then we also leverage kind of monotonic relationships that we know or assume should exist in these action value plots, where the closer you are to getting a first down, the more valuable it is. And likewise, the closer you are to the end zone, the more valuable it is. So we do this bivariate monotonic smoothing to leverage those relationships. And that leads to these decision maps that, they don't have these kind of weird islands in it, look a little bit more reasonable. So this slide here shows all of the entire candidate space of quantile optimal policies, at least ranging from 0.1 to 0.9. We don't look beyond that because there's some weird stuff estimating those really the tails. And I've vectorized each policy from the 2 dimensions to 1 dimension and show each quantile optimal policy by a column here. Okay, so we've got our candidate space now. Next, we need to choose a loss function whereby we will compare observed decisions to the candidate space. So we use a weighted Hamming distance, where these weights are just the differences in the quantile action values between the observed decision and the quantile optimal decision. And often those agree, right? Often, like this, if AJ equals AJ star, then the loss will be 0. But when it's not, it'll be weighted by the difference in the quantile action values. And then finally, I've got the dots shown here just to say that we index this loss, we calculate this loss indexing over observations, not like the average or the most frequent thing that they do in that state. Okay, so finally, we've observed that coaches' 4th down behavior tends to change whether the kicking alternative is a punt versus a field goal attempt. And so because of that, what we do is we fit separate quantiles to this field goal range, which we've, discretized here between the 31 and 40 and the 41 to 50 yard lines, and then a tau2 so we call this the field goal attempt region and the punt region here. And so now, we just minimize the loss over this candidate space and get curves that look like this, where we calculate the loss at every quantile, and then we just take the minimum, what minimizes the loss. And so for Bill Belichick, the quantile policy that minimizes loss with his observed decisions in the punt range is the 0.32, but you can see here that it's basically a flat line from 0.1 to like 0.38. And likewise for the field goal range, where here it's a bit more clear. The 0.1 quantile actually at the boundary is estimated as the closest quantile optimal policy to his observed decisions. Finally, to put some uncertainty intervals on these taus, we take bootstrap samples at the game level, and then so take all those games as a bootstrap sample, estimate the quantile action value distributions from the bootstrap sample, and then just do this process over and over again. So we get like all of these curves, and for each curve, the tau hat for that bootstrap sample will just be the minimum of that curve. Okay, so to go into our results, I'm going to show you a season by season analysis, a coach specific analysis, and analysis conditioned on 3 win probability bins. So first of all, season by season analysis. Here's the league average behavior from 2014 to 2020 on 4th down. And the color just represents the most frequent decision in that state. And here are the box plots that correspond to our bootstrap analysis of the estimated quantiles that these decision maps correspond to. And so you can see here that in the field goal range, there appears to be some more willingness to be a little more aggressive. I mean, we're nowhere near anywhere in like the risk-seeking area of quantiles. But actually for 2020, the median is actually right, the median estimate is right at 0.5. In the punt range, there appears to be like almost no change in behavior, at least on the league average. And it's all quite conservative. So coach-specific analysis. I've got the 40 coaches with the most fourth down decisions shown here. And here is the estimated quantiles with associated uncertainty, the box plots for each coach. And I show which team they had the most fourth down decisions with, because there's some coaches who changed teams over this period. And what I've shown here is the team that's associated with the majority of their fourth down decisions. But anyway, like similar results, a lot of estimates in the low quantiles, but there does appear to be a little more variation in the field goal range than the punt range. And there were only 2 coaches in the field goal range who had a median estimate above 0.5. Which again, not surprising, but kind of interesting for us to see. Finally, we want to like filter situations into the estimated win probability, because you can imagine, and as shown here, what a coach does on fourth down depends on like the score differential, essentially the win probability. And so here we do an analysis based on fourth down situations where the estimated win probability was low, where it was a little bit more of a toss-up, and where it was a blowout. They were winning by a lot. And you can see that it appears they're more aggressive when the win probability is low, which makes sense. And indeed, that shows up in the estimated quantiles where and this is across all coaches, but here we have estimated quantiles above 0.5 when win probability is low, but then it becomes conservative again when the game's more closer to a toss-up, and conservative when they're winning by a lot. And then in the punt range, even when they're down by a lot, there still appears reticence to be aggressive with respect to the fourth down decision. So to conclude, I do want to highlight some limitations. There's obviously potential confounders at play here. Team strengths, like we don't have enough data to estimate these value functions and action value functions with respect to individual teams. And of course, that would change with the kickers too. If you've got a bad kicker, that's going to change your decision. We have this highly discretized state space, yard line groups, and integer yards to go. And then, of course, it's probably not fair to, like, we're not trying to say causally that this is a coach's risk preference. There's other things at play here. Perceived risk of getting fired, group dynamics, don't want to go against what like everyone else in the league is doing. But I do feel like this method is a more principled way of kind of trying to measure apparent risk preferences. And not surprisingly, coaches and teams appear risk averse, conservative, though that does appear to be changing. And interestingly, there seems to be a lot more risk aversion when the kicking alternative is a punt rather than a field goal attempt. And I think as data analysts, this can help us better understand why coaches may deviate from our prescriptions, to kind of try and think about their optimization, their risk preferences. So anyway, I think that could be valuable. And here's some of the future work we want to do. Of course, we want to condition like the season by season analysis and the coach specific analysis also by those win probability groups. And hopefully extend this to other sports and other domains. So here are my references, and be happy to take any questions if there's time.
Thank you very much, Nate. Very interesting. there any questions? Time for a question or two.
Yeah, and people should put them in the Q&A or the chat.
Okay, let's see. Question here from Stuart. Sometimes the teams are in a must-win situation, e.g. a loss or a tie, and they're out of the playoffs. Are they more aggressive towards maximizing points or maximizing win likelihood, or no observed difference? How about whether it's the first quarter of the game versus fourth quarter? Yeah, so it brings up a great question here. And this kind of gets at the thing I was saying in my last slides, which was we want to use win probability of like the estimated win probability of the game situation as kind of a surrogate for a lot of for variables that we don't have in our state space, and estimate these risk preferences for coaches when they're in a must-win situation, versus when it's more of a toss-up or when it's a blowout. But I'm sure that we'll find variation when we do that. And I wish we had that now, but we didn't get quite the time to run it. But yeah, great question. We plan to kind of look at that. I know Mark has his hands up. There's another question here in the Q&A. I'll read that one. Was the analysis based on regular season data or also? So this was based entirely on regular season data.
Mark, did you have something else, Mark?
Yeah, no, I had a question. Have you, Nate? This is really fascinating stuff. Have you? So I know you were focusing just on quantiles. Had you considered expanding the summaries to things like kernel estimates, just to incorporate a little bit more of the variation of the distributions?
Yes, we've looked at a couple other risk measures. One of them being like expected shortfall. I guess that's actually the only other one we've really looked at. But we've kind of been running with the quantile just because it seems sufficient to differentiate coaches and to kind of measure risk preferences without having to be too complicated. And so yeah, it's a little bit more interpretable. But yeah, we'll see kind of when we submit this if we'll need to change that. But yeah, we've looked at expected shortfall.
Yeah, part of the motivation of my asking really was just noticing there was quite a bit of variation in the let's say the coach results based on the quantile. So I was wondering maybe if there's some other measure that's going to reduce that variation. It would be more compelling. But in some ways, it's just kind of sort of getting lucky and choosing the right risk measure.
Yeah, that's a good point, though. We should look at some others to see how the results change.
Let's take one last question you see there in the chat from Andrew.
Okay.
And then we'll move on.
Is there a reason why the field goal distribution doesn't have all the mass on 2-point estimates? That's a great question. So I put a kernel density estimate over those point masses just for ease in this presentation, really just for ease of explanation. But the analysis are all based on discrete distributions. You can imagine that these next state value distributions are discrete, and the state and the support is the number of elements in the support is equal to the number of states that are possible to transition to, and then there's a probability mass associated with each state. And so yeah, these distributions are all discrete in the analysis, but I have these KDEs overlaid because I felt like it just helps people understand and see these distributions a little easier. But yes, specifically, there is a point mass at the field goal make and a point mass at the field goal miss when we actually compute the results that I showed you.
All right.
Nate, you may want to answer the remaining question in just directly in a typed answer when you get a chance.
Okay.
Yeah.
Okay.
Thank you, Nate. That was really interesting.